Let's do a nice application of the strong law of large numbers. We're going to prove something really fundamental and something that you already intuitively um, understand, but you've never seen a rigorous demonstration of, and you've probably, yeah, you haven't seen the tools to do such a thing. What we're going to prove is that the distribution of values in a sample gets closer and closer to the distribution of values in the population that sample was drawn from as the sample size increases. Seems like a basic idea, but is it really true in a precise mathematical sense? Yes, it is, and we'll see exactly the sense in which it's true. That's what we're going to prove. So, to set it up, let x be a random variable with CDF, capital F, x of little x, as usual notation for the CDF of a random variable, and let x1, capital X1, capital X2, capital Xn be a simple random sample of values of x. Remember, that means these are independent, identically distributed random variables with the same distribution of x. They represent values taken from this distribution independently, right? So they all have the same distribution of this guy, and they're independent. And now we define this thing, capital F hat n of little x, as the proportion of sample values that are smaller than or equal to little x. So I count up the number of values in my sample that are smaller than or equal to little x, and I divide by the total number of sample values. That's called the empirical distribution function. So it's the function where you give it an input and it spits out the proportion of sample values smaller than or equal to that input. So that's the basically the version of a CDF, but for the sample. So now I'm counting the number of values in my sample that are smaller than or equal to something, and yeah, dividing by the total number. Show that this empirical distribution function converges to the distribution of x, CDF of x, as n goes to infinity with probability 1. So we're going to use the strong law of large numbers to do that. So first of all, let's discuss this kind of graphically. Just make sure that the setting is clear. So imagine that you have this random variable capital X. Let's just say maybe it has a PDF that looks like that. Now if you take a sample of values and you try to describe the distribution of that sample, well, you only have a finite number of values, so it's going to be a PMF, not a PDF. And if you were to actually graph it, it's not very helpful to graph the PMF of your sample. Because, say you took a sample from here, you're going to get some values between 1 and 2, some between 2 and 3, some between 3 and 4, and you're going to get more values between 1 and 2 than between 2 and 3, and more between 2 and 3 than between 3 and 4, in general, if you take a big sample. So if you were to actually try and graph the PMF, it would be something kind of silly like this. You would have just all these lollipops, all of the same height, but you would get lots of them, this forest of lollipops, all of the same height, 1 over n, where n is your sample size. Would be denser here, right? Because you're getting more values between 1 and 2. But if this guy is a continuous random variable, this distribution is a continuous distribution you're sampling from, then you're never going to get a repeated sample value that happens with probability 0. And so this is not a great way to picture the distribution of values in your sample, okay? This would be, I guess, if you were to give this a name, F hat. Maybe let's say, how many did I take? 1, 2, 3, 4, 5, 6. So I took 6 sample values. So if you were to try and define the PMF of your sample, it would look like this, but that's not really a nice way to visualize it. What you could do instead is like make a bar graph. That's a nicer way of visualizing it, where you just make the height of the bar. Maybe I'll make bars between each whole number. So I'll have a bar from 1 to 2, a bar from 2 to 3, a bar from 3 to 4, and the height of the bar will be the number of sample values in each of those pieces, each of those ranges. So I'd have a bar of height 3, a bar of height 2, and a bar of height 1, right? So if I were to do that, it would look like this. Maybe something like this. So that's a nicer way of visualizing the distribution in my sample. However, I guess here's 3. The scale here is kind of arbitrary. And also this decision to make the bars 1 unit wide was also kind of arbitrary. But it's still true that this bar graph, if you take bigger and bigger samples, it should have this shape of this bar graph should look like the shape of the distribution you're sampling from, right? And it should look more like it as the sample of values gets bigger. However, this is still, because of all these technical details, this is not going to make for any nice, we don't want those mathematical, those just details that we happen to choose for the purpose of visualization to enter into our mathematical arguments. So instead, let's consider the CDF. So if I were to draw the CDF of this guy, I think it would look something like this. All right. It's got this asymptote at 1. So this is f capital X little x. So remember, this tells you the proportion of sample values smaller than or equal to each input, each little x here. So if I plug in 3, I'll get this number like, I don't know what it is, 0.9 or something. That means 90% probability that when you pick a random value of capital X, it comes out to be smaller than or equal to 3. Now this empirical CDF that we defined, empirical distribution function, it's a really natural thing. So what we do is we take our sample and draw this asymptote in. We take our sample, and what we do is we draw a graph of the proportion of sample values that are less than or equal to little x for each input little x. And if you think about the graph of that looks like, all that's going to happen is you're going to go along 0, 0, 0, 0, 0, and as soon as you get to a sample value, let's say you're taking a sample of size 10. As soon as you cross the first sample value, then 1/10 of your sample values are smaller than or equal to that. So your graph is going to bump up to 1/10. When you cross the next sample value, it's going to bump up to 2/10, etc. So you're going to get like a staircase where the height, trying to do a good job here, the height of each stair is the same, but the lengths of the stairs might be different. So this is a f hat 10 of little x. I don't need to draw it all the way there. So this empirical CDF, empirical distribution function, is going to have 10 steps. The height of each step is 1/10, and the length of each step is just the distance between the 2 consecutive sample values that are closest to each other, right? So the idea, what we're going to prove, is this function, as n goes to infinity, converges to this one. So we'll have smaller and smaller steps and more of them. And as the number of sample values, n, this goes to infinity, this graph should approach this one. So here we go. Let's pick some number little x, all right, on the x-axis. Let's just use any little x. So take any little x, any real number little x, all right? And define indicators yi for the event that capital Xi is smaller than or equal to that number, little x. And this is, of course, for I equals 1 up to n. So for each of my sample values, capital Xi, I define an indicator, capital Yi, that indicates whether that sample value came out to be smaller than or equal to little x. So yi, this indicator, it takes the value 1 if that happened, and 0 if not. So if capital Xi is bigger than little x. That's what an indicator does. Okay. Now, because each of these xi's, each of these sample values, has the same distribution as capital X, each of these y's also have the same distribution. Because the probability that these things happen, the probability that, say, y3 comes out to be 1, is the probability that x3 is less than or equal to little x. But that's the probability my third sample value is less than or equal to little x. And there's nothing special about the third sample value. The probability the seventh sample value comes out to be smaller than or equal to this number, it's the same thing, because each of my sample values is drawn independently from the same distribution. So, the yi's are independent and identically distributed. Okay? Furthermore, it's easy to calculate the mean, the expected value of any of these yi's. Because to calculate the expected value of a thing, you just multiply each of its possible values by the probability that those values occur. So I'm going to multiply 1 by the probability this happens, and I'm going to multiply 0 by the probability this happens, and add them up. So, I did that up here. I'll do it again. So, the expected value, so you can see it happen, all right? And follow it more easily. The expected value of yi is going to be, remember, we're going to take each of the values and multiply by the probabilities they occur. So 1 times the probability of this plus 0 times the probability of that. It's going to be 1 times the probability that xi is smaller than or equal to little x plus 0 times the probability that xi is bigger than little x. And well, 0 times anything is 0, and 1 times anything is just that thing again. So I end up with the probability that xi is smaller than or equal to little x. But xi is, for any value of I, for any particular, say I equals 3, the third value in your sample, the probability the third value in your sample is smaller than or equal to little x, that's the same as the probability x. That's a random thing taken from the population, because the third sample value is a random thing taken from the population, is smaller than or equal to little x, because the distribution of xi is the same as the distribution of x. But this is just the definition of the CDF. The CDF of a random variable spits out the probability that it's smaller than or equal to whatever input I put in the CDF. So the probability capital X smaller than or equal to little x, that's the definition of this thing right here. The CDF of capital X evaluated at little x. All right, so what do we have? So the yi's are independent, identically distributed, IID, the abbreviation for independent and identically distributed random variables. With mean, we just calculated it, mu equals fx of little x. And that's exactly what I need to apply the strong law of large numbers. Some sequence of independent, identically distributed random variables with a mean that exists. So here I go. Now I'm going to apply the strong law of large numbers. So applying the strong law of large numbers, oops, it's a weird N. Applying the strong law of large numbers to the sequence of random variables y1, y2, y3 to yn, we have that the probability that the limit as n approaches infinity of the sum of the yi's divided by n, the average, equals mu the mean of the distribution that they're drawn from, in this case the mean of the distribution that they share, is 1. All right. Now, looking at these things, the way we define them, this is going to exactly work out. What is the sum of these indicators? The sum of y1 plus y2 plus y. Each of these indicates whether my sample value came out to be smaller than or equal to little x. So each takes the value 1 when that happens and 0 when it doesn't. So this is a 1 just when the first sample value is smaller than little x. This is the second, y2, this is a 1 when the second sample value is smaller than or equal to little x, and so on. So I'm getting a 1 whenever I have a sample value that's smaller than or equal to little x, and I'm adding them up. So what I'm doing is I'm counting how many sample values are smaller than or equal to little x, right? Because I get a 1 every time I have a sample value that is, and I get a 0 every time I have a sample value that's not. So in the numerator here, I have the number of sample values smaller than or equal to little x. That's what the sum in the numerator computes. And this mu, this is the mean of the distribution, the shared distribution of all of these yi's, which we just figured out up here, is f capital X of little x. And what is this? The number of sample values smaller than or equal to little x divided by n. That's the proportion of sample values that are smaller than or equal to little x. And that is this thing we defined in the question. That's this thing, the empirical distribution function, capital F hat n of x. So this thing right here is just capital F hat n of little x. And so filling everything in, look what we got. The probability that the limit as n goes to infinity of the empirical distribution function at x is this equal to the CDF of x at x is 1. So that's exactly what we wanted to prove. That as n goes to infinity, the empirical distribution function converges to CDF of x. That works at every value little x. So what I'm saying here is that for any real number little x, the height of this graph at that real number and the height of this graph at that real number, if I compare these two heights, as n goes to infinity, this one will get closer and closer to that one. And that's true at any number on this axis. So therefore, this function converges to that one. Because to say that two graphs are the same is the same as saying that for any x value, the y value you get is the same.